This is Babak. In this video I'm going to solve the following problem for you. Let me read the problem for you first. Evaluate the following double integral I equals to this double integral of this function, where r and theta refer to standard polar coordinates and d refers to the disk, a radius r centered at the origin. This integral arises when one wants to calculate the electric potential at a point on the rim of a disk of radius r that is uniformly charged. If you want to know how this integral is relevant to this physics problem, you can click on the link below this video. That would be a good idea if you pause the video at this point and try to solve this problem yourself first. If you do everything right, the final answer that you will get is I equals to 4r. r is the radius of the disk. Okay, now let me solve this problem for you. So here, let me draw a picture here. So here, assume that this is my disk, and these are the coordinate axes. And then say, for example, I have a point inside my disk with the polar coordinates r and theta. So assume that this point here has coordinates r and theta. First of all, I want to use symmetry to write this integral in a little bit simpler way. So if I just want to open this integral into an iterated form, so this is easy. So then I would write the integral d theta and then integral of the function in terms of r. Yes, and then theta goes from 0 to 2 pi, and r, little r, goes from 0 to capital R, the radius of the disk. But I'm claiming that instead of writing from 0 to 2 pi, I can simply write 0 to pi and then double this integral. Why is that the case? Because, for example, if you consider the mirror image of this point with respect to the x-axis, I will get this point, yes? And if I ask you what are the coordinates of this point, you will immediately answer the same r, but the angle is 2 pi minus theta, yes? Because this angle is 2 pi minus theta. But the point is that the contribution to this integral coming from this point is exactly equal to the contribution to this integral coming from this point. Because first of all, you see the r coordinates are exactly the same, but even though the theta coordinates are different, but cosine theta is not sensitive to this transformation. Yes, because cosine of 2 pi minus theta is exactly equal to cosine theta. So if I only confine myself to angles from 0 to pi, I am ignoring these points. But I know that the contributions from these points are exactly equal to the corresponding contributions coming from contributions coming from the corresponding points. So it means that I can just go from 0 to pi, but I need to multiply the result by 2. This will facilitate a little bit the coming calculations. If I don't do this, you will see I always need to take care about absolute values, which would be annoying. So this would be 2 times integral from 0 to pi this time, d theta, and then integral from 0 to r, dr, divided by this square root. Yes? Okay. Now let me give this integral a name and try to calculate this integral. So I will take this one j. My goal is to calculate j. Calculating j. Okay, so in this integral, theta is considered to be a constant because the variable of integration is just little r. The first thing that I want to do, usually in physics, it's always better to write something in terms of dimensionless quantities. So if I want to calculate j, I would factor r squared, the capital R squared, out in the denominator. So this becomes 0 to r. Then I will have dr. Oh, sorry, I have forgotten to write this r here. I have r dr, and then I divide the numerator and denominator by capital R. Yes. In the denominator, I will have this. R will go inside the square root, so it becomes r over r squared. Then I would write the term containing the cosine, so it becomes 2r over r cosine. And then finally, r squared divided by r squared is 1. Yes? So I have divided the numerator and the denominator by r squared. So if I have this divided by r, so this becomes this. Whatever is inside here, I divide by r squared. So I wrote this. But now what I do, I will introduce a new variable. So I would say let r over r be u. Then this means that r is ru, and this means that dr is r du. But now my r variable goes from 0 to r, so this implies that the u variable goes from 0 to 1. Yes, I put 0 here, you get 0. I put r here, r divided by r is 1. So then this integral can be written in this form. So it becomes the integral from 0 to 1. Instead of r over r, I put u. And instead of dr, I put r du. So this becomes u times r du. And then in the denominator, I will have a square root of u squared minus 2u cosine theta plus 1. Yes? And then what I do, I will pull this r out. So this becomes from 0 to 1, u du, and then what I have is square root of u squared minus 2u cosine theta plus 1. So because I don't want to carry this r all over with me, let me give this new integral a name. So let me call this new integral k, for example. Yes. And then let me write here that j is r times the k. Yes. So for the future. Yes. So now calculating k. So now I want to calculate k. These are standard integrals, but they are tedious to calculate. Yes, so I would say that k is equal to integral from 0 to 1. In the numerator, I will write 2u minus 2u minus 2 cosine theta plus 2 cosine theta, and then divided by the same denominator. I will just explain right now what's going on. U squared minus 2u cosine theta plus 1. Then I also multiply by 1 over 2, and then I will have my du. Let us see what's happening. First of all, these two will cancel, and I will get 2u, and that 2 will be cancelled with this 1 over 2, and I will get u, and then I have exactly u. So what I have written here is completely correct. Then I will separate my integral into two integrals. One of them, this one divided by this, the other one, this one divided by this. But this one is a constant because the integration variable is u. So if I decompose my integral, so it becomes equal to 1 over 2 integral from 0 to 1 2u minus 2 cosine theta divided by that square root sign, u squared minus 2u cosine theta plus 1 du. Then I will have 2 cosine theta will go out. This 2 will cancel that 1 over 2. So it becomes cosine theta integral from 0 to 1 du divided by that integral. Yes. That's a square root sign. So now I have two more integrals to calculate. So you need to be patient for this problem, okay? So I will call this one, for example, m, and I will call this one n. Okay? So then this means that my k integral is equal to 1 over 2 m integral plus cosine theta times n integral. So let me write this here for the future reference, okay? But now I want to calculate each one of them. So remember, what is m integral? So I will move it to the other page. So m integral, so let me write calculating m, yes? So what is my m integral? So m integral is the integral from 0 to 1, then I have 2u minus 2 cosine theta, and then divided by square root of u squared minus 2u cosine theta plus 1 du. So let me double check, yes? So 2u minus 2 cosine theta, yes, 2u minus 2 cosine theta, this one, and then integral goes from 0 to 1. That's correct. Now hopefully you realize why this was useful, because now I can do a change of variable, yes? I can say let u squared minus 2u cosine theta plus 1 be equal to a new variable. Let me call it x. Then let me by the way, I want to make sure that we are not confused with positive or negative signs when we take square root signs. So let me take this one to be x. So this clearly makes x positive. Then I raise this both sides to power 2 before differentiating. So this becomes this. And now I differentiate both sides. So the left-hand side becomes 2u minus 2 cosine u. I'm just differentiating with respect to u variable times du. The right-hand side becomes 2x dx. But my variable x goes from my variable u goes from 0 to 1. This implies that my x variable goes from where to where? Let us check. When u is equal to 0, this term and this term will vanish. Then I will have square root of 1, which is 1. So the lower limit for the x variable is equal to 1. But what would be the upper limit for x variable? If I put u equal to 1, then what will happen? This becomes 1, and this becomes 1, and this also becomes 1. So I will get 2 minus 2 cosine theta. But let me simplify that. So then this becomes 2, 1 minus cosine theta, but then hopefully you remember this formula. It is 2 times 2 sine squared theta divided by 2, but this 2 and this 2 will be multiplied, so it becomes 4. And then, it becomes 2, because after square roots it becomes 2, and then you will have the absolute value of sine of theta over 2. This is why I told you it is better to use the symmetry. But do I need absolute value sign here? No, because I realized my theta is supposed to go from 0 to pi. It's in the first and at most in the second quadrant. Yes, but when I divide it by 2, then it becomes in the first quadrant, and sine theta is guaranteed to be positive. So I really don't need to put any absolute value sign here. So it's very important. So the upper limit is just simply 2 times sine theta over 2. So it becomes 2 sine theta over 2. Okay, now let me put everything back to calculate m. So m becomes integral. Instead of 0 to 1, I would write 1 to sine theta over 2. Yes? Now instead of 2u minus 2 cosine theta times du, I have this expression. I can write 2x dx. And in the denominator, I have just x. But this is super simple now, because this x and that x are simplified, so I will get 2x as my integrand. sorry, I will get 2x as my primitive function. Then it's supposed to be calculated between 1 and 2 sine theta over 2. Yes, so then it becomes 4 sine theta over 2 minus 2. So I was able finally to calculate m. So let me change my color. So m is 4 sine theta over 2 minus 2. But the main challenge in this problem is not calculating m, but calculating n. So let me go to the previous page. So you see, I want now to calculate this n, which is the same integral with numerator equal to 1. Okay? So let me write here calculating. This is a real challenge actually. It's tedious. Calculating n. So let me write my integral. So integral is equal to integral from 0 to 1 du divided by square root of u squared minus 2u cosine theta plus 1. Okay, but this is also a standard, so that's a quadratic polynomial under a square root sign. Hopefully you know what to do. I need to make the complete square, so how should I do that? So let me work on it a little bit. So u squared minus 2u cosine theta plus 1 can be written as u minus cosine theta to power 2. But let me see what's going on. The first one to the 2, u squared, that's good. 2 times the first one times the second one, that is this term, that's also good. But the second one to the 2, it's cosine squared, which I don't have it. So it means that I need to subtract that to compensate for what I have added. But at the end I have a positive 1. But this can be written as u minus cosine theta to power 2 plus sine squared theta. The reason is that 1 minus cosine squared theta is nothing except sine squared theta. So therefore, and then I can use this, let me see if I can do it more efficient. If I take sine squared out, okay, so yeah, let me just do it so in 2 steps. So n becomes equal to the integral du over square root of u minus cosine theta squared plus sine squared theta, and then I have from 0 to 1. Now I introduce a new variable, so let us take u minus cosine theta to be y. Then immediately this becomes clear that du is dy. And then when u goes from 0 to 1, then y goes from minus cosine theta to 1 minus cosine theta. Yes, so this integral becomes integral from minus cosine theta to 1 minus cosine theta. And then I will have dy divided by square root of y squared plus sine squared theta. And I take sine squared out, then what will happen? So it becomes minus cosine theta, 1 minus cosine theta, and then this becomes dy. What I do, I will take square root, and then I will take sine squared theta out. This becomes y squared sine theta squared plus 1. But what I can write now, okay, now I will take sine squared out from this square root sign. In principle, I should write absolute value of sine of theta, but because theta is between 0 and pi, you see how powerful symmetry arguments are. I can just simply ignore sine absolute value, because when I am in the first and then second quadrant, sine is positive and I don't need absolute values signs. If I haven't done that before using the symmetry arguments, I need to consider 2 cases all the time when it comes to absolute value. Okay, so Here we don't have any problem, so I will take this one out. It becomes 1 over sine theta, and then I will have minus cosine theta, minus cosine theta to 1 minus cosine theta. In the numerator I will have d, and in the denominator I have a square root that I can write it in this form, y over sine theta to power 2 plus 1. Then I introduce a new variable again. I would say that let us take this one to be capital Y, then dy becomes sine theta dy. Yes? And now when little y goes from minus cosine theta to 1 minus cosine theta, this would imply that y, the capital Y, goes from minus cotangent theta to 1 minus cosine theta over sine theta. Why? Yeah, it's simple. What? Because this is my definition of the capital Y variable. So when y is minus cosine theta, instead of this I put minus cosine theta, but cosine over sine is cotangent and I have a negative sign. And the same thing for this one. But let me just open a little bit of a space here so that I can calculate this, make it a little bit simpler. This, I'm just talking about this upper limit. 1 minus cosine theta over sine theta, if you remember the formulas, it can be written as 2 sine squared theta over 2 for the numerator, and the denominator can be written as 2 times sine theta over 2 cosine theta over 2. And then what happens, this 2 and that 2 are cancelled. One of these signs and this sign are cancelled. What is left is one sign in the numerator and a cosine in the denominator with the same arc. So then this becomes tangent of theta over 2. Yes? As simple as that. So let me just close it here and then go back to the problem. So this means that my y variable goes from minus cotangent theta to tangent of theta over 2. So therefore the integral is equal to 1 over sine theta integral from minus cosine theta to 1 no, I should write cotangent, sorry. I should write minus cotangent of theta to tangent of theta over 2, and then instead of d little y, I can write sine theta times d capital Y, and then divided by square root of y squared plus 1. Then what happens, this sine theta for this integral is a constant. It doesn't depend on the variable of integration, it goes away, and then I am left with simply this expression. So n is equal to integral from minus cotangent theta to tangent of theta over 2 dy over square root of y squared plus 1. So let me go to the next page and try to calculate this one. So now I go here, so let me rewrite the integral. Integral was from minus cotangent theta to tangent of theta over 2. And then I have d capital Y, then divided by square root of y squared plus 1. Yes? But this is a famous integral, so this becomes a sine hyperbolic inverse of y from minus cotangent theta to tangent of theta over 2. But hopefully you know that sine hyperbolic inverse of x can be written in terms of the logarithmic function as this, which is more useful in this context. So I will do that. So it becomes equal to the ln of capital Y plus square root of y squared plus 1 from minus cotangent theta to tangent of theta over 2. But I need to replace y with tangent, replace y with cotangent, and then subtract them. But I know that the ln of the difference of ln's can be written as the ln of a fraction. Yes? So this is why I prefer to write it as a fraction, so it becomes ln of tangent theta over 2 plus square root of tangent squared of theta over 2 plus 1 divided by minus cotangent theta plus square root of cotangent squared theta plus 1. Yes? This would be the n integral, but I can simplify it a little bit. If you remember these formulas, 1 plus tangent squared x can be written as secant squared x. 1 plus cotangent squared x can be written as cosecant squared x. Okay, but here in this one becomes secant squared theta over 2, but I have a square root of that. Again, I face with an absolute value, but that is not a problem here. Theta is between 0 and pi, but when I divide it by 2, it becomes between 0 and pi over 2. It means theta over 2 is in the first quadrant, and secant is 1 over cosine theta over 2, so it means that secant is positive in the first quadrant, so I don't need the absolute value sign at all. And for the same reason here I don't need absolute value, because this becomes cosecant squared theta, and when I take a square root sign it becomes cosecant theta. Theta is between 0 and pi in the first and the second quadrant. Cosecant is 1 over sine theta, but in the first and second quadrant sine is positive. So again, I don't need the absolute value sign. So you see how powerful the symmetry argument is indeed here. So what I do, I will simplify this a little bit. So this becomes, let me write with the same color. So this becomes the ln of tangent theta over 2 plus secant theta over 2, and then divided by, let me write this term first, which becomes cosecant theta minus cotangent theta. Yes? So that would be the integral for me. I want to write the denominator of this a little bit simpler. So let me write with different colors. So cosecant theta minus cotangent theta can be written as 1 over sine theta minus cosine theta over sine theta, yes? And then this becomes 1 minus cosine theta over sine theta. But this is exactly the expression that I just calculated in the previous page. Do you remember here? So I realized that 1 minus cosine theta over sine theta is equal to tangent of theta over 2. Okay, so what I do, I would write this equals to tangent of theta over 2. And I go back to my original color, so this becomes, finally I will get this. So n, let me write this with different colors. So finally n is this expression. It's ln of tangent of theta over 2 plus secant of theta over 2 divided by tangent of theta over 2. Of course, I can simplify this a little bit more, but I'm looking ahead, so I want to keep it in this form. So this is my n integral finally. Okay, so now if you remember, we also had the m integral. The m integral was 4 sine theta over 2 minus 2. Let me write them, then I will show you to refresh your memory, and then this is a very long problem. Then we had a k integral, which was 1 over 2 m plus cosine theta n. Yes, so if we go back here, you see this is my m integral here. And then here, where was it? Yes, it's previous page. So the k integral is this integral, is this one. And then j integral is r times k. And then j times, so j is the integrand that I have to put here to calculate I. So I is equal to 2 integral from 0 to pi d theta j. J itself is rk, yes, it's here. J itself is rk, and then r goes out. So just let me write this on the last page. So what I am looking for is that my I integral is 2r integral from 0 to pi, then k integral d theta, where k is this k. Okay, so I need to calculate this now. So what should I do? Let me go back to my original color and start calculating this. I will have a 2r, and then I will have integral from 0 to pi. Instead of k, I multiply m by 1/2. So this becomes 2, this becomes 1. 2 sine theta over 2 minus 1. And then plus cosine theta times n. This is my n, so this becomes cosine theta multiplied by ln of tangent of theta plus secant of theta over 2 divided by tangent of theta over 2. And then, and then at the end, I put a big pair of brackets, and then I will have d theta. So in that case, I don't need to put this bracket here. Let me fix it. So this becomes 2r. Calculate this integral now. So I can decompose this integral into the first one, the second one, and the third one. Of course, it is clear that only the last one is problematic. Okay, so it becomes 2r. Then I will have the 2 integral from 0 to pi, and then sine theta over 2 d theta, and then I have minus integral from 0 to pi d theta, and then I will have integral from 0 to pi, this big integral, cosine theta ln of tangent of theta over 2 plus secant of theta over 2 divided by tangent of theta over 2, and then you have d theta. Yes? Okay, the first integral is very simple, so this becomes just minus 4 cosine theta over 2. Theta goes from 0 to pi. The second one, theta, it goes from 0 to pi. And the next integral, let me call this integral, say, z, for example. This becomes z. I will calculate z later. So then this becomes 2r. If I put pi, it becomes 0. If I put 0, it becomes 1. So the first one is 4. The second one is minus pi plus z. Okay, so finally I got this. My integral I that I am looking for is 2 times r, 4 minus pi plus the integral z. So I need to focus my energy on calculating integral z. Okay, let me go to the next page for calculating z. So z is integral from 0 to pi cosine theta ln of tangent of theta over 2 plus secant of theta over 2 divided by, what was that, tangent theta over 2 d theta. And I can decompose this into 2 integrals. Yes, the integral, because ln of a fraction can be written as ln of the numerator minus the ln of the denominator. So this becomes cosine theta ln of tangent theta over 2 plus secant theta over 2 d theta, and then minus integral from 0 to pi cosine theta ln of tangent of theta over 2 d theta. So again, let me give these names. So for example, let me consider this S, and let me consider this to be T. Okay, now let us calculate S. Okay, so how should I calculate S? For S, I use integration by parts. Actually, I used integration by parts for both S and T. So I will take U to be ln of tangent theta over 2 plus secant of theta over 2, and I will take cosine theta d theta to be dv. Okay, then I need to calculate du. So the du is this, the derivative of ln, which is tangent of theta plus secant theta over 2. In the numerator, I have to put the derivative of the denominator, which becomes secant squared theta over 2. The derivative of tangent is secant squared, but I have also to multiply by the derivative of the argument. And then the next one, the derivative of secant is just secant theta over 2, tangent theta over 2. The derivative of secant is secant times tangent. And then I also have to multiply by the argument of this, the derivative of the argument d theta. But this can be simplified quite a lot, yes? I can factor 1 over 2 secant theta over 2. What is left from the first term is just simply this. What is left from the second term is this one. And then I divide this by the denominator. But you see that this expression is exactly the expression that appears in the denominator. So this one and this one are cancelled. I also have d theta here. So this means that finally, let me write it here, du is equal to 1/2 secant theta over 2 d theta. So this is my du, yes? And then, of course, this is very simple. Because cosine theta d theta is dv, it is clear that v is just sine theta. And then let me just write the formula for integration by parts. Integral of u dv is equal to uv minus integral v du. And of course, if you have the limits, you should also put the limits here and there. Okay, so what I do, the integral that I am looking for, integral from 0 to pi cosine theta ln of tangent theta. Oh, let me write s. It's easier. So s, integral s becomes equal to u times v. This is my u, this is my v. I multiply them, so it becomes sine theta ln of tangent theta over 2 plus secant theta over 2 from 0 to pi, yes, minus integral from 0 to pi of v times du. v is sine theta, my du is 1 over 2 secant of theta over 2 d theta. Okay? But here I will have a problem when I want to put the upper limit. So I need to take the limit and send theta to pi, yes, to see that if the limit converges or not. But I do not have any problem with 0, yes, because secant of 0 is just 1, tangent of 0 is 0, so this becomes 1, ln of 1 is 0, sine of 0 is this one. So what I want you to calculate first, I have to calculate the limit of this function when pi theta goes to pi. But I can also simplify this a little bit so that to make it easier to calculate. So here I want to calculate the, let me simplify this expression a little bit and then I will take the limit, yes? So if I want to simplify this expression, I would write it in this form. So ln, instead of tangent, I can write sine theta over sine theta over 2 over cosine theta over 2. Instead of secant, I can write this. And then what happens? This becomes sine of theta ln of 1 plus sine theta over 2 divided by cosine theta over 2. Then I can write it as the sine theta multiplied by ln of the numerator minus the ln of the denominator, but I also have to multiply by sine theta. Yes? But if you see, I do not have any problem here. If theta goes to pi, this becomes 1, pi over 2, yes? Plus 1 is ln of 2, which is completely defined, but sine of p is 0, so this becomes 0. So the only thing that I need to calculate is what is the limit of this part when pi goes to 0, because theta goes to pi. Because in that case, this becomes 0, and then ln of 0 is infinity, and this is 0. So what I want to do, so this is what I told. The limit of this function that I was looking for, calculating its limit, when theta goes to pi is this one, the limit of this part, which is 0, minus the limit of that part. So this is the minus limit of sine theta ln of cosine theta over 2. Okay, so let me calculate when theta goes to pi. I think it would be easier if I introduce a variable, so I will introduce the phi variable to be this. Then this becomes minus the limit. When theta goes to pi, phi goes to 0, and then sine of theta becomes sine of pi minus phi, and then I have ln of cosine of pi over 2 minus phi over 2. So this becomes minus the limit of sine of pi minus phi is just sine of phi, and then I will have ln cosine of pi over 2 minus phi over 2 is just simply sine of phi over 2, and phi goes to 0. So don't forget about what we're doing. We have to calculate this integral, we have to calculate this limit. But I can use the Hopital's rule to calculate this limit, then I will come back and calculate s. Okay? So I am supposed to calculate minus the limit phi goes to 0 of sine of phi, what was that? Sine of phi times ln of sine phi over 2, yes? But then let me write it in this form. The limit phi goes to 0, instead of sine phi I can write 2 cosine phi over 2 and then sine phi over 2 ln of sine phi over 2. Yes, but the limit of this part is just simply 2 when phi goes to 0, so I need to concentrate and calculate this limit. Yes, so I need to calculate this limit. Phi goes to 0. But then I can take this sine of phi over 2 to the denominator, so it becomes ln of sine phi over 2 over cosecant of phi over 2 when phi goes to 0. Then I use the Hopital's rule, so the derivative of the numerator is simply sine phi over 2. The derivative of sine phi over 2 is 1 over 2 cosine phi over 2. And then the denominator, the derivative of cosecant is minus 1 over 2 cosecant of phi over 2 cotangent of phi over 2. And then phi goes to 0. But this is nothing except cotangent of phi over 2, so this one and this one are totally gone, and this 1/2 and this 1/2 are gone. So what is left for me is another minus sign, which is 1 over cosecant of phi over 2 when phi goes to 0. But this is nothing except a sine of phi over 2 when phi goes to 0, and this becomes 0. So the limit of this part is 0, the limit of this part is 2, so the limit of the product is 0. So finally we were able to show that the limit, this part, so this part is totally 0. Because for 0 it was 0 easily. For pi we also showed that this is 0. So this boundary term is totally gone, and I am left with calculating this one. So let me take this one with me to the other side so that to calculate. So it means that s, the s integral, is exactly the value of this integral. Okay, so I will take this with the minus sign. Okay, I will take this to the left, the other page. So therefore, my s, I will have this here, yes? This is my s. This is my s. But then I can simplify this, so I can write minus integral from 0 to pi. Instead of sine, I can write 2 sine theta over 2 cosine theta over 2 multiplied by 1 over 2. Instead of secant, I would write 1 over cosine theta over 2 d theta. And then what happens is that this one and that one are cancelled, 1/2 and 2 are cancelled, so I will left with minus integral from 0 to pi sine theta over 2 d theta. Yes, and then what is this one? It becomes minus a positive 2 cosine theta over 2 from 0 to pi. If I put pi, it becomes 0, so it becomes minus 2. So my s integral is finally minus 2. Okay, I need to do something similar for this t integral, and then you remember this is the subtraction at the end for calculating z. So let me write that one here so that we are not confused. So my z integral is s minus t. So far I know that s is minus 2. Now I go and calculate t. So the t integral, I will take it here. So t integral is equal to integral from 0 to pi cosine theta ln of tangent theta over 2 d theta. I will do the same thing. So I will take ln of tangent of theta over 2 to be u. Then I calculate, I want to use the integration by parts again, as I said before. So this becomes tangent of theta over 2, then 1 over 2 secant squared of theta over 2 d theta. And if I simplify this, it becomes so it becomes sine over cosine, and that's sine squared. So let me write it. It was too long, so it is cosine squared theta over 2, and then the denominator I have sine theta over 2 cosine theta over 2. So one of them is cancelled, so it becomes 1 over sine theta. Yes, because one of them and this one is cancelled, this will go to the denominator, this will also go to the denominator, I will have that combination. And then I will take cosine theta d theta as before to be dv, so immediately I can see that v is just sine theta. So integral t is uv, but what is u? U is ln of tangent times v, which is sine theta ln of tangent of theta over 2 from 0 to pi minus the integral from 0 to pi of v times du. But v times du is very simple, it's just d theta. Okay, but again I need to calculate the limit. Yes, so I have to calculate the limit here. So let me just do it like this. So this part I need to calculate the limit actually in both sides. So sorry. So here the limit I want to calculate is this limit of sine theta ln of tangent theta over 2 when theta goes to pi, because I will have problem on both sides now. Yes, and then I also have to calculate the limit of sine theta ln of tangent of theta over 2 when theta goes to 0. Yes. Okay, so for example, the first one I can let me write this L1, limit 1, let me call it limit 2. So limit 1 is the limit of sine theta. Instead of ln of tangent, I can write ln of cosine minus ln of sine. Yes, but then I multiply this. Yes, so this is the limit that I want to calculate when theta goes to pi. But this is exactly what I just calculated in the previous problem. Yes, you see sine theta ln of cosine theta over 2. So if we go to the previous problem, that was the limit that I calculated. Yes, that was the limit. Sine theta ln of cosine theta over 2 when theta goes to pi. Yes, so this limit is 0, but when I send pi equal to 0, there is no problem here. Sine of pi over 2 is just 1, ln of 1 is 0, so this becomes again 0. Okay. For this one, we can also do the same, similar things. Okay, so if you continue, you will also find that L2 is equal to 0. So this means that again this boundary term is completely gone, and what is left for me is just minus pi. Okay, now let us go back. Do you remember my z is s minus t? So s minus t. So my z is s minus t, so let me write it here. z is s minus t. What is s? S is minus 2. What is t? Is minus pi, so it becomes pi minus 2. So this is my z. I need to take this z with me and put it in here. So therefore, let me copy and paste this one with me. Take this one with me. This was my let me write it here. Yeah, it was a very long problem. I'll make it smaller. So this is my z. I now put it here. I hopefully haven't done anything wrong, so let us see how it goes. So I becomes 2r, 4 minus pi plus pi minus 2. And then exactly this pi and that pi are cancelled. 4 minus 2 is 2, and 2 times 2r is finally 4r. Yeah, it was a super tedious integral to calculate directly. The only thing that I haven't shown explicitly is the calculation of this limit. I hope that you can also do this using similar methods to show that this limit is also indeed 0 and everything we have done is completely rigorous. I hope that you enjoyed the video. I will put this PDF file of my solution actually below this video in the descriptions. So if you want, you can download and just review what was going on in solving this problem. And I also, as I told you, I will put you the link to a video which motivates why this integral comes into our game in the first place, why I was interested in calculating this integral. Okay, until the next video, be safe and goodbye.